to this to show a practical example of k-means, how we can use this with the library that we have been using so far. So I'm going to put this example also in online, and then you can play with this. So sometimes a couple of things that you have to take in mind. You might need to install a couple of few extra libraries. So basically, you need to install this library, and for this, what you have to do is to type install packages and this clue. You have to install this. I'm not going to do it because I already did it in the before, and this one as well. This one is a little bit difficult, so you might have a few problems with this one in particular if you are working with Mac, probably Linux as well. This is only for visualizing to get something like this figure that we have that I'm describing here that we have here in the video. So if you don't have, if you cannot manage to install this, that's fine. You don't need this. You can just comment this line, and then that should be fine. You won't be able to see the figure, but you still can compute the clusters. Okay, so basically, I'm going to be using these libraries that the popular library Machine Learning R that we have been using for a while, and this is just for visualizing the clusters. Okay, so this is a clustering problem, so I'm going to be using the popular IDs data set. Remember that this is a very popular academic data set, and remember that this is unsupervised clustering. So we are going to remove the target label because we don't want to use that. All we want to do is to create the clusters and to play with the k-means method. Okay, so basically I'm going to remove the target feature. This is the target feature. And now we are going to be building the clusters. Okay, so basically we're going to be telling the library that we want to use the IDs dataset. Okay, so then we use the make cluster task, and data is going to be equals the data set that we're going to be using. In this particular case, we are talking about the IRIS data set. The value of k, the number of clusters that we want to have. Now we use the make learner. We tell the library that we want to use the k-means. Another there are other clustering techniques. We are only going to cover, for now, we are only going to cover k-means and k-medois in a minute. And okay, now we are going to tell the library that we want to have this number of clusters. In this case, it's 3. Now we build the model. Remember that sometimes you have to do this because there are lots of implementations of machine learning. So we want to use the machine learning R, the one that we have been using in the past. So probably you don't need this, but if you had any problems, so just only try to include this piece of code. We tell the system that the library that we want to use k-means, and this is the data set. And all we have to do now is to say get learner model, and then we get the output here. This is basically how we can process the data in order to create the clusters. Okay, and basically now if we want to visualize this, to get a visualization of this, we're going to be using plot learner predictions, and we are going to be seeing we will be getting a figure like this. In this case, this is 4 because I tried this before, but give me just a second. I'm going to be executing this. Let's go up to here. I'll explain let me just do this again. Okay. So basically what we have to do now is, I just want to visualize this. I just recompute the figure, and this is the output that we get. As we can see, basically response is going to tell me that we have 3 clusters, 3 different colors. So this is the red one is going to be the cluster 1, the green one is going to be the cluster 2, and the blue one is going to be the cluster 3, because we indicate that we want to have 3 clusters. And basically this is the output. If we change this, for example, if we say 4, then we will be getting, of course, a different figure. Basically now we have 4, as we can see here. This is basically because of the random starting combination of the random location. It could have been different depending on the random initial location of the clusters, of the centers of the clusters. We can also say it's 6. I mean, you can start playing with this, and then you will be seeing different potential solutions. Okay, so in this case we are going to be selling 6, so we have 6 clusters. Let me just go with a small value. Okay. We go back to 3. The solution can change a little bit depending, again, probably you will be seeing a different solution depending on different colors. It probably will be more or less similar, but that depends a lot in the initial position of the centers. Now, if we want to have a look at the location of, of the centers, we have to use the output of getLearner model. In this case, it is variable res, and then we can say there is a lot of information here that we will be using. In this particular case, all we want to have a look for now. If you want, if you're curious about this, you can play with this later on. Basically, centers is going to tell me the actual location of the centers because we have three. So these are going to be the centers of the clusters. So for example, this one here is going to represent the blue one, sorry, the green one. And so the second one is the second one is in this case the third one, and so on and so forth. Okay, if we have more, for example, if we have, let's say, 6, then we will be seeing that we have just give me 1 second, centers. Then we see 6 because we're going to be seeing, let me just update the figure, and then we see that we have the centers of the clusters. These are going to be the centers of the clusters. Now, if we want to compute the total distances to the centers of the cluster, it's actually the square distance, we can use this piece of code in order to compute the total sum squares. For example, if we want to use the elbow method in order to identify the optimal value of the optimal value, no, a suitable value for the number of clusters, if we cannot say that beforehand. Okay, for that, so basically this is going to be the piece of code that we're going to be executing. Probably you saw that here. Okay, the total sum square. This is going to be the value for this particular value of k. A couple of other important things. For example, if we say we want to know the cluster of all the samples, clusters, and then this is going to tell me that the first sample is going to be in the second cluster, that the second sample is going to be in the sixth cluster, and so on and so forth. Okay, so basically this number indicates the cluster for that particular sample that we have. Okay, so now if we want to have a look at the elbow method, we can easily implement this. Let me just quickly delete this. Oh no, let me just quickly start a new one. I have that code there. Just 1 second. And basically what we have to do, I'm going to be this. And let me just give me 1 second. This is just a piece of code. It's also in the slides, and you can have a look at this. But this is a piece of code in order to it's a naive implementation of the elbow method. Okay, so basically we are telling the library, we are telling the system that we want to try values from 1 to 30, and basically what we're going to be doing is we explore k equals to 1, k equals to 2, k equals to 3, and so on and so forth. And then just let me quickly error that I'm getting here is because I need to tell the system that I'm going to be using. So you see, this is the kind of errors that we get in this. Sorry, it's not. It is actually here. This is the kind of errors that we get because there are multiple implementations of train in R. Okay, so I want to tell the system that we want to use this one in particular. Okay, so basically now we're computing these values. Okay, so basically what we do is that we compute the value for 1, 2, 3. This is the total cumulative distances, square distances to the center of the cluster. And as we can see here, let me just quickly increase the size of this. We can see the plot, the figure with the respective values. For example, a good option here could be For example, k equals to 5 looks like a very reasonable. Any point from 4.5 to 10 would be very reasonable options for values of k. Here we see a massive improvement. Remember that we are always going to be seeing, or most of the time we're going to be seeing a massive improvement in the objective function when we have k equals to 1 to 2. That's when we see a huge improvement, and then we are going to be seeing a small improvement. Is not going to be that huge, but still we can see here reasonable improvements for this approach, for the elbow approach.